introduce Robert Hargraves, who is our speaker today for the first Jones Seminar of this academic year. He will be speaking to us. His talk is called Aim High, and the topic is thorium-fueled nuclear reactors and a power industry that would possibly develop from that. It's a very interesting topic. I had a chance to chat with Dr. Hargraves before this seminar, and I think you will find it very interesting. Robert Hargraves is a Dartmouth graduate. He got a AB in both mathematics and physics from here. He did not hesitate to go for the hard stuff. He also went on to get a PhD in high-energy physics from Brown University, and worked in a number of places, including at Boston Scientific and Arthur D. Little, and also a company that was founded and owned by Dartmouth at one time called DTSS, Dartmouth Time Sharing System, an interesting computing development. Somewhere in between, he was also a professor of mathematics and director of the Kiewit Computation Center here at Dartmouth, and is currently now teaching in the ILEAD program, the Institute for Lifelong Education at Dartmouth. Please welcome. If I make another announcement, out of consideration for our speaker, please refrain from using laptops. Thank you.
As you'll soon see, Aim High is a project with lofty goals. I'm presuming that you know all about global warming, and I'm not going to consider that issue anymore, except to say this is a problem we want to address. Another problem we have is the resource competition for water and for food. Most of the large fish in the ocean are gone. We have a big problem with resource competition, which sometimes leads to war. This is a picture of the Gulf War with Iraq and Kuwait. Another famous faculty member from the Thayer School was Dennis Meadows, who wrote Limits to Growth back in somewhere 1972, where he did modeling on the Dartmouth time sharing system about the state of the world, resource consumption. You'll notice population goes up, and then in his model, somewhere around 2040 begins to crash. He was widely disparaged at the time because people said, well, wait a minute, Dennis, technology has always saved us in the past. People have always said this, and we always manage to develop some new technology that provides the energy or the food. You're too pessimistic. But in fact, an article in the American Scientists earlier this year went over his predictions and pretty much confirms that he was just about on track. Now let's take a look at population growth. This is from the OECD, the Organization for Economic Cooperation and Development. It projects a world population near 9 billion in 2050. But if we look at the growth of population in the OECD nations and the US, you'll notice it's a lot flatter. Why? I did a scatter plot. I took data from the CIA World Fact Book, and I plotted for 83 countries over 10 million the number of children per woman and the GDP per capita, which is very closely related to income per capita. And when you look at that, you notice on the lower right that the very poor countries are the ones that have all the children and all the population growth. The stable population replacement rate is about 2.3 children per woman. On the left of that red line are those nations that have populations that are actually declining or stable. And to the right, that the low-income countries, we see where we have many children per woman. I see that about $7,500 per year is what I call modest prosperity. Those nations that have modest prosperity are the ones that have the low birth rates. So it's if we could somehow help the nations that are below that modest prosperity achieve it, they would just very naturally stop having so many children. Prosperous countries allow women free time from just chores and food gathering and so on, time that they can use for education, for job seeking, and for making their own choices about reproduction. But prosperity depends critically upon energy. And in this graph, I show energy in terms of electrical energy. This is annual kilowatt hours per capita, again from the CIA World Fact Book, available on the internet, and GDP per capita. And you see that, in fact, the income goes up somewhat linearly with kilowatt hours per capita. And in fact, that modest prosperity level we spoke of before at about 7,500 corresponds to about 2,000 kilowatt hours per year per capita. That's about a sixth of the usage. The US is off here on the right off the screen, about 12,000 kilowatt hours. Now, the developing nations want more energy. They want prosperity, and they're going to get that energy from coal. These are the projections for non-OECD energy use as the developing nations prosper. What went wrong here? Oh, I see. As the developing nations prosper, and there you see that coal is expected to grow, even in the United States, by the way. Many people say, well, we consume too much energy. We need to stop. There's negawatts available. Let's have the soft energy path. And in fact, conservation is the only short-term solution we possibly have at hand. So it's very important. But here's the US using 3.8 petawatts per year. Petawatt hours per year. Let's just hypothesize that we're able to cut our consumption in half from 12,000 kilowatt hours per year per person to half of that, going down to 1.9 petawatt hours. But the rest of the world wants to prosper as well. And if they all try to achieve that same level of electric use, which is half of what the US uses, you can see that energy consumption is going to grow fantastically, from 15.4 worldwide to about 37. Now, carbon taxes aren't enough. Here's an economist, a famous economist from Colombia, who has been the advisor to the governments of Russia and Bolivia, who is an author of the Millennium Development Goals, and who is the special advisor to the Director General of the United Nations. He says carbon taxes aren't enough. He's concerned that increasing the price of energy will stifle the economic growth of the developing nations, which is critical for them to achieve the kind of prosperity that allows for human development. We need more than a price on carbon, and the technologies that we develop in the new world, in the rich world, need to be adopted rapidly in the developing world as well. So I say, okay, let's have a new energy source. All we need is a new energy source that produces electricity cheaper than from coal, and I'll go into that later on in the talk. The idea here simply is that we want to undercut the price of coal. We don't seem to be successful at raising carbon taxes, certainly not worldwide, so that's a goal. Another aggressive goal is to synthesize vehicle fuel and to have a fuel source that is inexhaustible, reduces waste, and is affordable to the developing nations, who are the nations that are going to be consuming more energy, and the nations we want to encourage to have a lifestyle like that of the OECD nations that has a low birth rate. Thorium, a plentiful fuel, That's a play on, the thunder and lightning is a play on Thor. There's a lot of it. There's enough in the US right in one few hundred acres plot for a millennium of power. But it's not a fissionable metal. How can it be a fuel? We need to do a little review. Here is a different view of a part of the periodic table. On the top, you see the labels on the columns are the atomic numbers of the elements thorium, protactinium, uranium, neptunium, and so on. And the labels for the rows are the atomic weights, the numbers of protons plus neutrons. And in that display, there are 3 fissionable fuels, one of which is found in nature, U-235. The others are U-233 and plutonium-239. Just reminding you about your physics for a minute here. What happens in a uranium reactor is that a uranium-235 nucleus is hit by a neutron, becomes unstable, and divides into 2 smaller nuclei, about half the size. In this example, krypton and barium, but there are lots of pairs that could be. Again, in this example, if you remember Einstein E equals m squared, we look at the mass of everything that went into this reaction, and then look at the mass of what came out, and you get 1.166 MeV of energy right away, a little more as the fission product. Okay. That's the basis of nuclear power, the fissioning of atoms into smaller pieces that releases energy. Now, in that same reactor that we have all over our country, other kinds of things happen as well. And by the blue arrow, I'm representing neutron absorption. In that neutron flux in the reactor, the nuclei of U-238 sometimes absorb a neutron, becoming U-239. But that's an unstable isotope, and that decays by beta decay, the ejection of an electron that changes the charge on the nucleus and changes the number of electrons around it, changing its chemical property. So that decays to plutonium 239 in this example, which is also a fissionable fuel. We actually breed that kind of plutonium today. In a standard nuclear reactor, about 1/3 of the power at the end of the fuel cycle comes from plutonium, not from the U-235. So we're already breeding that. In the same way, thorium-232 can absorb a neutron, become uranium-233, beta decay over a few days to become uranium-233, a fissionable product. So that's how we breed uranium fuel from thorium. The words you might see sometimes are and fissile. The fissile materials are the 3 we talked about. The fertile ones are the ones that can be made into fissile fuel. Here's the diagram of the inside of a conceptual reactor that uses uranium-233. In that yellow inner core is the normal critical reaction, the fission reaction, that releases neutrons that make other U-233 atoms or nuclei fission, but there are extra neutrons that are left over that flow into the green thorium blanket of 232, where they are absorbed, and some of them make more U-233 out of that thorium. The thorium is sent off to a chemical separator, part of the reactor plant, which extracts chemically the 233 uranium. Remember that the uranium has a different chemical property than the thorium, so you can put a chemical plant together to extract it. That is then fed back into the fissile core. At the same time, a similar kind of circuit takes place where the fission products from the fission of the core need to be separated and taken away, and a chemical separation process similarly removes them chemically. of course, the whole thing generates heat, which is used to make steam eventually. It runs a turbine that spins a generator that makes electric power. Now, there's another important thing about the liquid fluoride thorium reactor. Not so much that it's just thorium. The other very important attribute is that the reactor fuel is dissolved in a liquid. A normal nuclear reactor has solid fuel rods. Here, the liquid that it's dissolved in is a molten salt of fluorides, lithium fluoride and beryllium fluoride. It has a lot of advantages. One is because it's a dense liquid, it has excellent heat transfer because the liquid can flow. Another advantage of this is that we can do continuous chemical processing of, on one side, the blanket to extract the uranium, and on the other side, the fission products to remove them. The whole thing is at atmospheric pressure. It doesn't need a 160 atmosphere pressure vessel to hold it. And if we're to leak out and cool, it's solid at room temperature. So these are the fundamental differences with a liquid-fueled nuclear reactor. Now, how do you get it started? We don't have any uranium-233. Well, we sort of do. We have some left over from the Manhattan Project. We have about 500 kilograms of it that the U.S. government is desperate to get rid of. In fact, they've already budgeted $500 million to dilute it with U-238 and bury it in the desert. We're trying to convince them to do otherwise. It would be a good way to do the research. But you could also prime the unit with any fissile material properly prepared. It could be uranium-235, which we can get, or even plutonium from spent light water reactor fuel. It's plentiful. Here, in this example, to scale a 1-ton sphere of thorium metal would fuel a city like Boston for a year. It costs the entire U.S. with your existing electric power plants could be replaced by 500 tons of this a year. It costs about $300,000 a ton, and the government just, again, back from the Manhattan Project, has 3,700 tons of it just as storage, but just sitting there in the desert with no particular use. And there's a lot more that can be mined. This is Lemmy Pass on the Idaho-Montana border. It has 1,800,000 tons of uranium ore right there. And here's the ore in the desert that we own. Well, if it's so good, why don't we have it now? Why do we use uranium pressurized water reactors? History. Eugene Wigner was a Nobel laureate at the time of the Manhattan Project, and he was the guy who schemed up the idea of breeding thorium to uranium. And Fermi had the idea of breeding uranium to plutonium. There were a lot of reasons, but one of which was that there are more neutrons created in this reaction, so it was easier to make more weapons material or more fuel faster. And our nuclear weapons technology was all built around breeding plutonium eventually. So the idea was well known, but not followed up on. They had to make a decision which technology to follow, and they picked this one. Now, Weinberg was a bright guy. He holds the patent on the pressurized water reactor. It wasn't awarded to him until years later because it was top secret. But you see other interesting signatures here, Eugene Wigner, Alvin Weinberg on this patent. And he convinced Rickover and Rickover's staff that the pressurized water reactor was the proper fuel for naval propulsion. And you all know that Rickover then, having been trained at Oak Ridge in about 5 years, built the world's first nuclear power reactor as an engine for an underwater submarine. Now, Rickover was a man with drive. He was very strong-willed. For example, he despised uniforms. He didn't wear a uniform. He got to be admiral in the Navy. And when Dwight Eisenhower gave the Atoms for Peace speech, he talked about nuclear power, and he tapped Rickover to create the world's first land-based nuclear power electric plant in Shippingport, Pennsylvania. And it was a design that was modified from a design that had been developed for an aircraft carrier. Well, that set in motion what today is over 100 United States pressurized water reactors and boiling water reactors. Now, what happens inside a nuclear reactor? On the left, you see what's coming into it. About 3.5% of the fuel is uranium-235. And on the right is all this stuff that comes out. You can see that there's 3% of the fission products representing the stuff that was burned up. And there's still a fair amount of potential energy in terms of the U-238 that might be used. Might have been. But it's solid. It's a solid fuel system. And one of the problems with solid fuel is that it's solid, and in the fuel rods on the right, the radiation, the fission products that are generated in the heat damage it. So here's the cracks and whatnot that are inside a cross-section of that fuel rod. The zirconium cladding on the outside of the fuel rod has to contain all those waste products for centuries. So that's the engineering challenge that the designers of the solid fuel rod have solved. What if we just left the fuel in there, left the waste, the high-level elements here? We make uranium, neptunium, plutonium. We leave. If we could just somehow leave it in the reactor for a long time, it would go away. Either one of these elements is going to get promoted, like plutonium to americium, by neutron absorption, or one of these elements is going to fission into two others and form one of the fission products on the periodic table. So if we could just leave it in there, we could do that, and that's what the liquid fuel reactor allows to happen. Now here's a quick review of liquid fuel reactors. The second reactor that Fermi ever started up was in fact a liquid fuel reactor. It had a sulfate of uranium in water, and the reactor was designed to determine the criticality, how much critical mass was needed to cause criticality in uranium. At the time, he had all the world's supply of enriched uranium. All the 235 in the world was at his disposal. So that's that. Later on, there was another kind of reactor that was developed at Oak Ridge, the aqueous reactor. It's called homogeneous because the uranium was homogeneously distributed within the reactor. And here's a picture of Richard Engel way back when adding a solution of heavy water with dissolved uranyl sulfate to the to the power reactor. And it worked. 300 grams of uranium gave power for 2 months. So that kind of technology was known. It didn't work as an electric power technology because the water solution was unstable at higher temperatures. Unbelievably to me, until recently, to discover that at Los Alamos they had a liquid plutonium reactor. That metal, in liquid form, powered a reactor for a couple of years. And off in Holland, yet another reactor, in this case homogeneous but not dissolved. It was just fine particles of uranium in a heavy water reactor, and that was a successful sort of reactor, but never came to commercial use. Meanwhile, Weinberg had another plan, and he got involved in a new project to develop the molten salt reactor that I alluded to before. The first time they built it over a period of a year or two, and it had the following characteristics. Hot, 860 degrees centigrade was what it ran at. A red hot reactor. They ran it for 100 hours, and it generated 2.5 megawatts thermal energy. Why did they do that? The reason was that Rickover and the Navy had created nuclear submarines that patrolled the world. The Strategic Air Command circled Russia, loaded with nuclear weapons at that time, and the planes had to be refueled, and the Air Force generals wanted an airplane that could be nuclear powered, that could fly indefinitely without refueling. And so this was the plan. That idea that was tested was put into a design of what's called the firewall reactor, 1.4 meters in diameter, generating 200 megawatts of thermal power to run those jet engines. These were designed but never built because ICBMs came about, and that was a more economical way to convey our nuclear threat to keep the world at bay. Now, even though Weinberg had suggested the pressurized water reactor to Rickover, he felt that the humankind's whole future depended upon this. He wrote about global warming from carbon dioxide emissions. And it was his idea that the fertile thorium could be wrapped around that kind of reactor to generate heat to make power. So he directed the Oak Ridge laboratory to do a molten reactor experiment between 1965 and 69. Here's some folks assembling the graphite core. And the experiment succeeded. Just taking a look at the diagram for a minute, you can see the graphite core in green on the sort of left there. This is an interesting thing. These are what are dump tanks, and that is, if the reactor ever overheats, the liquid salt would fall into these containers in a non-critical configuration. Then you see a heat exchanger and the normal sort of generator off on the right, not shown on the diagram. Hastelloy was an alloy which was suitable, it turned out, and proven to be suitable for structural materials for this sort of reactor. One thing that happens in a reactor is that one of the fission products is xenon, and it absorbs neutrons. So you want to get it out of the reactor as fast as you can, if you can. And in this case, they were able to bubble out the xenon as it was formed in the liquid fuel. So that test worked well. The graphite was suitable. They developed pumps, fluoridation equipment, dump tanks, the whole kit and caboodle. They ran it not only with U-235, but also with U-233, just to make sure that that would happen. So over a period of years, that thing ran 17,000 hours. So it was a successful experiment. Not a lot of power. It didn't say here. So I say, okay, my topic title here is Aim High, and I'll explain why as we get into it. Aim High says, let's develop reactor core in the blanket. Weinberg did the yellow core, never did the blanket, never got the money, the project got canceled. There's a lot of engineering to be done. The uranium separator, the fluorination equipment, the waste chemical processing, a heat exchanger. The hotter we can make this thing, the more efficient it is. Carbon composites are suitable materials, hopefully, for heat exchangers. The turbine and generator. We're looking here at a Brayton cycle turbine, which the South Africans tried hard to build. A cooling tower, a nice control system, and maybe if we get it hot enough, maybe 900 C, we can do very efficient hydrogen separation. Plenty of engineering work. I also say, develop a small modular reactor that can be transported to the site. And the cost objective that we'll come to in a little bit is $200 million for a modular unit. That way it can be affordable to developing nations. The World Bank might even loan somebody $200 million. They might not loan $2 billion for a really big plant. We'll have power sources that are distributed with low transmission line costs, with less vulnerability to terrorism or storms. And we can gang multiple units together for large power plants so that utilities can make incremental capital investments as the demand rises. I also say we can use air cooling. A typical power plant, like the ones around here, evaporate 20,000 gallons of water a minute, or perhaps warm a river by the 600,000. Because the liquid fluoride thorium reactor runs hot, we can actually have the heat loss, making it more practical to do air cooling. And you've probably been reading the papers about complaints about nuclear power plants heating up the river. Wherever water is in short supply, we could convert to air cooling at a little bit of cost of efficiency. And the other problem we have is, I'm wondering about the public reception. Is it possible to make a graceful looking power plant? Maybe. But if you can't, just paint it. What about the control system? Well, you know, we have airplanes that can fly themselves. We have public transport systems that run without operators. We can have high reliability systems for automated unattended operation, and we can have physically passive systems like the Molten salt system with the freeze plug that prevents any kind of a problem in the event of a loss of the control system or electric power or something of that nature. There's another important thing, and that is to reduce the number of on-site workers. That lowers the operational costs. It lowers the risk of safety overrides. Remember that both Chernobyl and TMI involve operator errors that perhaps could be designed out of the system. Another one is costs. Look at Vermont Yankee here, 600 megawatt system with 600 employees. That's over a penny per kilowatt hour just for the labor costs. There's another important thing about this, and that is that since the U-232 has such a much lower mass number, only 232 compared to plutonium-239, it takes a lot of neutron absorbers to make something like your plutonium or other high-level wastes. So, for example, in this diagram, which is log-log, notice, first look at the blue line. The fission products are hot. The ones that they're very radioactive. The ones, when you take fuel out of a reactor right away, it's very radioactive. It has to be cooled in water in a typical plant for years. But after a few hundred years, it stabilizes at a relatively low level. And that dotted line in the middle is the radioactivity of natural uranium ore that will be needed to operate such a plant. So you get some idea about how that stabilizes. Now, the red line at the top is the long-lived radioactivity from elements like plutonium, americium, neptunium, all those heavy ones. But in the LFTR, liquid fluoride thorium reactor, those elements aren't happening. In fact, so there's 10 to the fourth less of these long-lived, heavy radioactive materials in a liquid fluoride thorium reactor. So it has a nice design benefit, too. It also, since we're burning all of it, not just 0.5, 0.7% of it, we get rid of a lot of the disturbance of the land, and we generate less waste. There's an example. Edward Teller, who was a longtime veteran of the Manhattan Project, got interested in molten salt, and he and Ralph Moore developed a proposal to have the government develop such a thing. And he worked on it until the last month of his life when he finally died. I subsequently contacted Ralph Moore, who's the co-author of that article in American Scientist. And there are some copies of that article in the back of the room that you can have if you like. So, what do we need? We need energy cheaper than coal. Prove it. Well, first of all, it's a crucial element of the strategy for aim high. And let's look at some things. One, Copenhagen failed. People did not agree worldwide to reduce carbon emissions via raising taxes or cap and trade. Hasn't happened in the US Senate. It's certainly not going to happen in the developing nations. The developing nations say, well, wait a minute, the OECD achieved prosperity through burning fossil fuels. We want our 350 parts per million in the atmosphere, then we'll talk about it. Or you can buy us off. One of those. That's what's happening. Coal, on the average, delivered to a power plant in the United States costs $40 a ton. If you multiply by the BTU per ton and the kilowatt hours per BTU, that's about 2 cents a kilowatt hour contribution. That's just from the coal. The MIT report says that an average new coal plant costs $2.6 per watt of capacity. That's another 2.6 cents a kilowatt hour. So we've got about 4.6 cents right there that we have to slide under. That's kind of what we need to do. Well, there were 5 independent estimates of molten salt reactor construction costs in the literature, and I inflated them all up to 2009 numbers. And you see the median's about $1.98, about $2 a watt of capacity, which translates to about 2 cents a kilowatt hour of contribution to the cost of the electricity. So we might get under there. Now, other reasons. The high thermal efficiency. Remember, it's because it's a liquid fuel, because that liquid molten salt has a very high thermal capacity. And because new things like carbon composite heat exchangers can allow us to run that temperature up beyond 800 degrees centigrade. Another reason is it's not so massive. Here's a picture on the left of a typical AP-1000-like power plant. You can see the orange pressure vessel in the middle and the enormous building around it that is there to contain any rupture. Remember, the pressure inside here is 160 atmospheres. That's a lot more than the scuba tank. And so you want to be sure that none of that radioactive material can get into the environment, so you'll build a big containment dome. There's a picture of a project being built in Japan, a GE project in this case. They're big. The crane will handle 1,000 tons. Here's the current AP-1000 being built in Xiamen, China, a few months old. And if you look down here in the middle, you see that red spot. That's a workman there. So it gives you some idea of the scale. If you can't quite see him, I'll blow him up. There he is. I'm guessing he's about 1.4 meters tall, because that's the size of the fireball reactor, about 1.4 meters. So you get some idea of the potential scale differences that could be achieved with that sort of technology. The Brayton power cycle, another important thing. I won't go directly into it except to say that it has never been achieved at commercial scale. There's a fair amount of R&D yet to go in it. It's high on the list of DOE projects. It was high on the list of the South African project, but that was never completed. It's like a jet engine, Brayton cycle, but here closed. Now I say, let's build these things. They're only $200 million each, like we build airplanes today. Boeing builds a $200 million airplane every day on the average. There's a production line. They just roll them off. They have the same issues we do in nuclear power. They have materials issues. They have quality control issues. They have fabrication issues. They have life safety concerns. We could build nuclear power plants the same way. The other important thing is the concept of the learning curve. And that is, as you produce more and more things in a factory, it's generally observed as you double the number of units produced, the cost drops a bit. The University of Chicago estimates it's about a 10% learning ratio in the nuclear industry. In most industries, it's about 20%. In the IT industry, it's 50%. So this is a pretty conservative number. And if we build one a day for 3 years, according to this concept, we really will drop that price about to perhaps 35% of what it was before. So let's do the math here. If it costs $200 million to build one of these guys, I borrowed my wife's little HP calculator and plugged in 40 years, 8% to get the levelized cost of this thing, and divided by the number of kilowatt hours it produces, and we get about a little over 2 cents per kilowatt hour contribution from capital. The startup fuel, I increased that price to $5 million, although we're buying it for $1 million today from Russia, but we're going to run out of that pretty soon. Thorium is trivially costly. Decommissioning costs, I said, well, put aside $100 million for the future. Well, plan on $100 million in the future. That's not much. And operations, I just made a swag. I just said, remember, I want to keep nobody there, but we got to have some budget for operations. So that's coming in at a little over 2 cents a kilowatt hour. That's good. We want to have a little room to undersell coal. What happens if we do that? We install one of these plants every day worldwide. We will zero emissions from coal plants in 38 years. All of them. What about vehicle fuel? Well, there's a process that helps to fracture water at high heat into hydrogen and oxygen. And you can use that hydrogen not as a fuel, it's a poor fuel. You can make ammonia to make fertilizer, which is responsible for 2/3 of the world's food. We can use it for methanol and gasoline, as advocated by George Olah, Nobel Prize-winning chemist, about the methanol economy. Or dimethyl ether, another thing for diesel fuel. So we can manufacture synthetic motor fuels. Now, it turns out we use a lot of fuel. I did the math. I said, well, suppose we did one of these a week and dedicated it to making gasoline. Well, we don't, even at the end of the century, we don't cut out very much of the gasoline. That isn't a great idea. The electric car works pretty well, though. Maybe half the fleet could be converted to electric cars. The heavy trucks and things couldn't, but small cars could. Chevy Volt, 8 kilowatt hours, about at 15 cents each. That's what, $1.20? You get your 40 miles. That's a lot cheaper than gasoline. And so that's the kind of thing you can do. But we're not going to make an electric jet airplane. We need to have that kind of fuel to make jet airplanes run. This is a big 777. Interestingly, each of those engines can generate 200 megawatts of kinetic energy. They're really big. We were talking about a power plant with only 200 watts of electrical energy. So we need that. So I say, okay, develop a prototype in 5 years. People say, well, that's kind of fast considering the rate of progress we've had now, except that we put a man on the moon in 2011. Rickover built the first ever power plant and put it in a submarine in 5 years. The Shippingport reactor was built in 32 months, and Weinberg engineered the X-10 in Oak Ridge, and that was built somewhere else in a 9-month period. So if we really work hard and we think it's an important thing to do, you can actually get things done quickly. Not only that, if we get to one a day, that's a $70 billion industry just for the power plant production, let alone the ancillary services. So that can solve our balance of payments problem. So, did we meet the aggressive goals? Well, I say yes, we did produce electricity cheaper than from coal. I think we can do it under 3 cents a kilowatt hour. Did we synthesize vehicle fuel? Well, yes, but not a lot of it. It didn't quite meet the goal as well as I thought we might. Is it inexhaustible? Yeah, there's a lot of thorium around. Does it reduce waste? Yeah, by a factor of 10 to the 4th. Is it affordable to developing nations? Well, we think so. At $200 million to get started, we might be able to bring those nations up to the level of prosperity that corresponds to a stable birth rate. So the ultimate objective is then check global warming and enable worldwide prosperity and population stability. But what are we doing about it right now? Not much. Here's what the U.S. spent in the past on the liquid metal cooled fast breeder reactor technology. Accumulating it all together and bringing it up to 2011 dollars is about 16 billion. That's the investment we made. Today's budget for next year says 103 million for what's called the next generation nuclear plant, which is a high temperature gas reactor with graphite pebbles fuels. That's been going on for decades. This 22 million for advanced reactor concepts, and I thought that would look good, but I looked in the budget notes and so on, and that's principally for fast reactors, the kind that we stopped supporting in the past. And there's $40 million for what's called advanced fuel cycles, but there's no liquid fuel and no closed fuel cycle. So the problem is big, there's a big solution to it, and we're making zero progress towards it from a government investment point of view. So I say, do this project. What are the benefits? Well, we could cut 10 billion tons a year of CO2 emissions to zero. We could avoid carbon taxes. We could improve world prosperity, check population growth, reduce radiotoxic waste, and consume some of the world fissile stocks to get these things started up. And use inexhaustible thorium fuel, which all nations have access to. Thank you.
Any questions from the audience? Why are we doing it?
Well, I think because Congress hasn't voted the money or endorsed it, because most people don't know about it. I gave a similar talk to this at the American Nuclear Society, and most of the people in the audience had never heard of this technology. So it's sort of under the radar right now, and I'm trying to change that a little bit.
So what about proliferation? If every country has thorium, what about proliferation?
Every country has thorium, and so conceivably every country could build one of these. So the question is, could that be used to make weapons? And I'm gonna put that question in context just for a minute. And that is that the biggest risk for nuclear weapons is from uranium-235 enrichment for power plants. You know that, for example, in Iran, there is an enrichment plant enriching materials to 3.5 or 10 or 20%. But just by running that plant longer, you can enrich it to 90% and make nuclear weapons. So that is what I see is the risk for nuclear weapons. In the recent months, the following countries have announced plans to develop their own enrichment plants: South Korea, Vietnam, Jordan, joining Brazil and Saudi Arabia. That's where it comes from. If a country really wants to build a weapon, they probably can. Look what happened. India was able to build a weapon all by itself with a heavy water moderator. Pakistan was able to do it by a centrifuge enrichment scheme that they borrowed from the Dutch. And North Korea was able to do it with a graphite reactor. So people can do that. So in the case of the, let me see if I got the right slide here. In the case of the liquid fluoride thorium reactor, I'm going to return back to this periodic chart for a minute. It's a little technical and busy, I'm sorry. But the point here is that inside that nuclear reactor, it just happens that a lot of that uranium-233 is changed to 232, which is a very hazardous material for weapons builders. And so, although it's conceivable you could put that stuff together, here are the problems they'd run into. First of all, the design we propose only breeds as much uranium as it consumes. So if you were to take some out, it would stop. So that would alert everybody. Second thing is that U-232 contamination is pretty high, 0.1% more or less. And it decays by a decay chain that eventually ends into a 2 MeV gamma ray that is deadly. a 5 kilogram sphere of this stuff would radiate about 10,000 times more radiation than a plutonium bomb. So it's not something that the defense industry wants to have nearby. After 72 hours of exposure, a meter away, you get enough radiation that you're likely to die from radiation sickness. So it's not a pleasant material to work with. But we need to have, checks and balances. We need to watch to make sure that in any nuclear plant, nothing like this happens. Very unlikely. So I say this will never happen because there are a lot less cheaper paths to follow. I was in Alaska, and you know the story about the hunters are out there, and they're being chased by a bear, and they're running along, and one guy stops and says, I'm going to take my running shoes out of my backpack and run. And his friend says, well, why are you doing that? You still can't outrun the bear. And he says, I only have to outrun you. We got this same thing here. No one's going to invest in a thing that won't work and is very expensive when there are technologies that have already been demonstrated by developing nations. So it might be possible to make a weapon. It seems very unlikely. And in fact, it won't happen because it's just too easy to do it another way. The other point is that if you did this, there wouldn't be very much demand for uranium enrichment plants. And so that would wipe off the table that sort of excuse for enriching uranium to make weapons. Questions?
What about the chemistry of lithium fluoride? Does that react, that has lithium, does lithium fluoride react with water?
I don't think so, but I don't know. I really don't know. The lithium fluoride is all in a sealed environment.
What I'm getting at is, could you conceivably put this reactor on, say, a ship?
Well, yes, and in fact, one of our senatorial candidates in Pennsylvania is introducing legislation, or has a couple of times, to try and get that done. So conceivably, it would be a good power plant. Please.
Maybe you're touched on it and I missed it, but did you show whether conventional nuclear power plants, whether the power from them is cheaper or more expensive than your thorium reactors?
The existing fleet of power plants generates power at around 4 cents a kilowatt hour. It gets marked up by the time it gets to your house, of course. But if you were to build new plants, they'd cost maybe triple that, because the capital cost was low in those days when they built all those plants.
Kind of two questions. Who owns the patents on this, and why haven't you sought the private enterprise?
I don't know who owns patents on this. I know there's a guy named David LeBlanc up in Canada who owns a patent on a nice internal reactor design. I'm sure there are patents everywhere. The business of intellectual ventures, which was founded by Bill Gates and Nathan Myhrvold, is to accumulate patents. So they've hired lots of engineers, and they are accumulating patents. They expect, they're working on a different technology, a kind of a U-238 conversion technology, but there's an example of a rather big investor who had the capability to invest in a new technology. All these things require a lot of government attention, though. You need to prime the NRC to be able to approve such a thing. You need to be able to use their test facilities to check out the fuel strengths and so on. I don't know.
Is 200 megawatts the optimum size of the LFTR reactor? Can it go smaller without losing some economies of scale?
I think it can go smaller. Yes, I do believe that. I just picked that number, not quite out of the air, but a lot of people argue with me that I don't understand economy of scale, and then I argue with them that they don't understand the learning curve. So that's an engineering problem.
I'm also thinking of the infrastructure for distributing that power in developing countries. That's a big chunk. That's why generation's only 1/3 of the cost of our power. So we need smaller size reactors so we can minimize that distribution cost.
Right, and also minimize the investment because the small countries can't come up with that $1 billion.
At the time they shut down the Oak Ridge molten salt reactor, stability of the under radiation conditions of the valence of the uranium. I never knew whether that was an excuse to shut it down or whether that was real. Do you have any information as to whether that's the molten salt system with the fuel in solution, whether that was stable under radiation conditions or whether they could actually play out critical bits in various places?
It ran for years, so it has that level of stability. The earliest experiment accidentally illustrated the fact that it does load following. They were dumping all the heat, what was it, 2.5 megawatts of heat, I think I said, into a kind of an external radiator that was red hot. And half that radiator failed. And so they only had half as much heat to get rid of, could only disperse half as much heat. But what happened in that sort of power plant is an intrinsic stability. As the salt heats up, it expands, squishes some out away from the critical area, and so it automatically load follows. And that was tested, not by design, but tested.
I was going to call this off. Maybe one more question.
You were talking about proposing more automated systems to have fewer workers in the plant area. But I recall the 1975 Browns Ferry fire when some of the control room wires burned and suddenly systems that they thought would be separately controllable, redundant systems weren't controllable because the insulation burned and then there were short circuits across the wires. I'm concerned about what I'd call like a Homer Simpson factor, in theory it might be great, but in actual day-to-day operation, would it be safe?
We need good engineers. All right.
Okay. Thank you all for coming.